Hello viewers, welcome back to our series of lectures on chemical bonding. In today's session, we will talk about ionic solids. We will focus attention on to the structural aspects of ionic solids. The session is planned as follows, that is, to begin with, we will briefly review what we did in the previous sessions. Having done that, we will try to revisit crystalline solids, about which we have learnt in our lecture series on crystalline solids over there or solid state over there. Having done that, we will come down to the main theme of today's session, that is the structure of ionic solids. We will begin with the salient features of such ionic solids over there. Having done that, we will move further and try to see what are the characteristic structures adopted by ionic solids of AX type. And then in this context, we will bring in the radius ratio rules and then see what are these rules, how do we apply them, and what are the limitations of such rules over there. And towards the end, we will try to sum up what we do in today's session. Now, let us begin by recalling what we have done so far. What we have done so far is, we started by introducing the concept of chemical bonding and discussed the classical theories of chemical bonding. Having done that, we moved on to the valence bond theory and outlined its limitations. Valence bond theory basically is a modern theory of chemical bonding. Having done that, we took up two different theories. One is VACPR theory and second the concept of hybridization, which basically is based on the valence bond theory. These two were used to kind of explain the geometry of molecules, and then towards the end we took up the concept of molecular orbital theory and discussed the approach for homonuclear and heteronuclear diatomic molecules. That is all what you have done so far. Now, let us move from here and then try to recall a few things before we come to the main theme of today's session. And those things are, firstly, you will recall from earlier sessions that according to the Cosel's theory, a bond formation basically involves transfer, that is loss or gain of electrons. That is, if I take the example of bond formation in sodium chloride, an electron from sodium atom is transferred to a chlorine atom, and what you get is that sodium loses an electron, whereas chlorine atom gains an electron, and both of them become ions there. Sodium becomes sodium ion, a cation, and chlorine atom becomes a chloride ion and an anion there. And these two charged species, they interact electrostatically. That means they are attractive to each other in terms of electrostatics, and this kind of electrostatic interaction between the two ions of opposite charge is what constitutes an ionic bond. And the compounds which are formed in such a fashion are called as ionic compounds or ionic solids for that matter. That is one bit we have to recall. Secondly, we want to bring in, since we are going to talk about the structures of ionic solids, we will try to recall something about the crystalline solids, which we learnt in our session on solid state over there. You will recall that in terms of crystalline solids, that is, the structure of metallic solids per se can be rationalized in terms of close packed structures. You will recall that we learnt about two types of close packed structures. One is called as hexagonal close packed structure and second is the cubic close packed structure. In case of hexagonal close packed structures, what will happens is that we got a layer of close packed spheres, and then these layers are alternating with each other, that is A, B repeat is there. Whereas, if the layers repeat in such a fashion that we got ABC repeat, what we get is a cubic close packed structure. We will not get into details of these things because that we learnt in the other series over there. We just briefly recall for ourselves because we are going to use this over here. You will also recall that CCP, that is cubic close packing structure, is actually equivalent to face centered cubic structure. That is the kind of picture we are having there. That means, if I have a cubic close packed structure, that will actually come down to the face centered cubic structure there. And in such a structure, important thing is that the coordination number is 12. That is, each atom is surrounded by 12 neighbors. That is, in case of a CCP, the 6 will be in the same layer, 3 will be above it, 3 will be below that. And further, the packing efficiency of such kind of a packing is about 74%. And thirdly, that in such a packing, since there are spheres are packed together, there are certain kind of holes called as interstitial sites or holes or voids, and that what we have is there are about one octahedral void or hole per sphere in case of FCC structure or CCP structure over there, and there are two tetrahedral voids per sphere in this structure there. They are the characteristic features of CCP or FCC for that matter, because we are going to use this here. Okay. Now, let us go further. In addition to these two, we also found that there are certain kind of non-closed packed structures also. One happens to be a simple cubic one. You see that in this case, the packing is not as compact as in case of HCP or CCP. And another option is, that is what you call as a body centered cubic structures there. And the important features of these two structures are, that is, in case of simple cubic, the coordination number is 6. That is, each sphere is having 6 neighbors to it, and the packing efficiency is of the order of about 52%. Whereas in case of BCC, the coordination number is 8 and packing efficiency is what, 68%. So, they are the possible structures what we have here. Okay. Going further, we also know that in case of crystalline solids, that any crystalline solid can be expressed in terms of a 3-dimensional lattice there, and such a lattice can be generated by repeating what is called as a unit cell. That means, you take a unit cell, repeat in all the 3 dimensions, we generate the whole lattice there. Okay. So, there are a few things which we learnt elsewhere. One more thing before we proceed further, that is, in case of cubic unit cells, there are 3 possibilities. One is simple cubic, one is BCC, one is FCC. And since we are talking in the context of metallic solids, we see that polonium is the one which crystallizes in terms of simple cubic structure. Iron, chromium, sodium and tungsten, they adopt BCC structures. Aluminium, lead, copper, silver and gold, they take up FCC structures there. So, that is as regards our metallic solids there. Now let us move further and come down to the structure of ionic solids. What you find is that similar to metallic solids, even ionic solids also tend to adopt structures with symmetric close pack arrangements of ions. In case of metallic solids, we had atoms which were packing together, and in case of ionic solids, we got ions in place of that. And when you try to pack ions, there are 2 things which become different. Firstly, that is, the size of ions is different, because what you find is, in case of metals or metallic solids, all atoms are identical, whereas in case of ionic solids, we find that the 2 ions which are constituting the ionic solid, they happen to be of different sizes. Typically, cations are smaller than the anions. And second thing is, the ions are charged species. That is again very significant difference over there, because in case of metallic solids, they all are electrically neutral atoms over there, and here what we are having is, we got charged particles there. So, because of this, there are some kind of differences will come into play. Now, let us move further and see, look at some of the salient features of ionic solids. The first and foremost thing is, the ions are charged, taken to be charged, elastic and polarizable spheres, and the cations are surrounded by anions and vice versa. That means, in any ionic solid, what will happen is, you will have got cations, we got anions there, and how are they packed together? What will happen is that these cations will be surrounded by the anions, and anions in turn will be surrounded by the cations over there, because that is how the electron neutrality will come into play. And what is important is, the 2 will be so closely packed, there will be minimal distance. That means, the opposite charges will have a minimal distance between each other. And secondly, the similarly charged ions, say anion or cation, they will try to arrange themselves in such a fashion that is, they are as far apart from each other, because that is from the stability reasons. If the 2 anions are coming too close, they will try to repel each other, the structure will not be stable there. So, they will try to have a maximum distance from each other, opposite ions as close as possible, similar ions as far as possible. And in order to maximize the net electrostatic attraction, because the stability of ionic solid depends on what is the extent of electrostatic interaction between the ions. So, if there are more ions of opposite type around a given ion, then there will be more electrostatic interaction. So, as a consequence, what we expect is, that is, in order to maximize that next electrostatic attraction between the ions, the coordination number are as high as possible. What it means is, that is, around a given ion, there should be as many ions of opposite type as possible. That will depend again on the sizes again. We will come to that. Okay. So, they are the salient features of the structures adopted by ionic solids. Let us move and see what are the characteristic structures for ionic solids of AX type, because when it comes down to ionic solids, we find that there are number of ionic solids available to us, and then when you talk about AX, AX2, AX3, basically we are talking about the species, say in case of AX, that means there is 1 cation, 1 anion. And in case of AX2, there will be 1 cation, 2 anions, and so on and so forth. So, there are variety of things possible there, but in our course here, we will try to confine ourselves to ionic solids of AX type only, that is 1 to 1, that is a 1 cation, 1 anion species. Okay. Now, the characteristic structures adopted by the ionic solids of AX types, there are 3 types of such structures. One is called as cesium chloride structure, second is the sodium chloride structure, and the third one is zinc sulphide structure. Basically, zinc sulphide comes in 2 different kind of structures, one is woodsite, one is zinc blende. In case of what we are going to talk up today is that is about the woodsite structure there. Now, let us talk about these structures one by one. We will begin with the cesium chloride structure, which basically is based on the simple cubic lattice, and this structure is adopted by the solids having ions of similar size. Like in this case of cesium chloride, cesium ion has a size of about 167 picometer, whereas chloride ion is about 181 picometer. They are comparable, about within 10% of each other. Now, what happens is in such a structure, the anions occupy the lattice points at the corners and the cations are at the center of each unit cell. That is, we have got 8 anions and cesium is sitting inside the simple cube over there. That is how it shows up here. That is, what you have is we got a cesium ion here and there are 8 neighbors to that which are on the corners of simple cube over there. But the important thing here is that is both the cation and the anions are surrounded by cube of 8 ions of opposite type. As I said, we got cesium ion here surrounded by 8 chloride ions there. Similarly, each chloride ion will be surrounded by 8 cesium ions over there. In fact, what happens is these 2 ions, they are in such a fashion that they form what is called as interpenetrating simple cubes. That means there is a cube of cesium ions having a chloride ion in the center of it and vice versa. And in such a case, the coordination number happens to be 8 for both the ions there, and similar structures are adopted by calcium sulphide also. Calcium sulphide also has a structure of cesium chloride type. That is one characteristic structure of AX type of ionic solids. Let us take up the second one, that is the sodium chloride structure, which is very familiar to you all. Sodium chloride structure basically is based on FCC lattice there, and in this case what happens is the chloride ions form the FCC lattice, that is they are the CCP sites there, and the sodium ions are in the octahedral voids or vice versa. Here again what we have is we have got now typically when we express the structure of sodium chloride, we say the slightly bigger chloride ions are the forming CCP, or they are occupying the face centered cubic sites there, and the sodium ions are in the octahedral voids. But same thing happens to be true for the reverse of it, that is we have got sodium ions at FCC sites there and chloride ions in the octahedral voids there. Now, this is adopted by solids with ions of dissimilar size. We see that sodium ion is about 97 picometers, whereas chloride ions are of about 181 picometers. The size difference is fairly large. Okay, let us move further and see that in case of sodium chloride structure, what we have is that the size consideration require that chloride ions to be surrounded by as many sodium ions as possible, because that is what we said earlier, that is the stability of the structure requires that the electrostatic induction should be as large as possible, and for that to be there we find we will expect that the larger chloride ion should be surrounded by as many sodium ions as possible, so that there is more interaction, we got more stability. But what happens is the charge neutrality is to be there, because sodium chloride is neutral species overall. So, charge neutrality requires the numbers to be equal. What we want from energy considerations, that there should be as many sodium ions around chloride ion as possible there. So, because of these two considerations trying to balance each other, we find that only 6 chloride ions can fit around the smaller sodium ions there. So, that is again a very important consideration there. So, as a consequence what you find is that in case of NaCl, each chloride ion is surrounded by 6 sodium ions and each sodium ion is surrounded by 6 chloride ions there, and both of them have a coordination number of 6 each. Further, what you find is a similar structure is adopted by number of ionic solids like KCl, KBr, AgCl, LiF, MgO and calcium oxide. All of them adopt similar structure to sodium chloride there. So, that is a very common structure adopted by different ionic solids there. Now, let us move further and take up the third characteristic type of structure adopted by AX type of ionic solids, and that structure happens to be zinc sulphide structure or called as Woodside structure. This structure also is based on the face centered cubic lattice, and the important thing here is that such a structure is adopted by the ionic solids having large size disparity between the ions there. We see that zinc ions are about 74 picometers, whereas sulphide ions are 184 picometers, which is much larger than that of the zinc ion there. It means anion is much larger than the cation there. And the structure is such that the largest sulphide ions, they form the FCC lattice, the main lattice over there, and the smaller zinc ions occupy alternate tetrahedral holes there. That is very important. What we, if you recall from our earlier session on solid state, we find that in case of an FCC lattice, there are in one unit cell, there are as many as 8 tetrahedral voids, and out of the 8 tetrahedral void, only 4 are occupied in case of zinc sulphide there. And that means, since there are 8 tetrahedral voids, every alternate tetrahedral hole or the void is occupied in this case. Now, as a consequence, since zinc ion happens to be in the tetrahedral void, so the coordination number happens to be 4. That means, each zinc ion is having 4 near neighbors as sulphide ions there. The coordination number is 4. A similar structure is adopted by number of solids there, that is cuprous chloride, silver iodide and cadmium sulphide there. Okay. Now, there are 3 structures which are typically adopted by the solids of AX type. Now, what is important is that how do we determine which structure will be adopted by which ionic solid, and for that we have a kind of a rule called as a radius ratio rule. And radius ratio basically is a parameter which is basically a determinant of the structure type of a given ionic solid there. And what you see is, typically if you want to talk about the structure adopted by an ionic solid, there are certain two determinants are there. First determinant is the relative size of ions, and second is the relative number of ions there. That is, when we talk about the size, we have been talking about the size in all these examples over here. When we come down to relative number of ions is when we talk about different types of ionic solids there, that is MX type, MX2 type, MX3 types. So, the numbers are 1, 1, 1, 2, 1, 3 and so on and so forth. And since we are focusing attention on to the ionic solids of MX type only, that is, we are talking about solids of 1, 1 type, that means there is 1, the cation anion ratio is 1:1. In such cases, we find that it is the size which is important here. The number is not relevant here, because we are talking about number is fixed as 1:1. Okay. If size is important, how do we bring in the size over here? Size is brought in terms of a concept called as radius ratio, which is defined as given as gamma to be equal to r small by r large. R small is the radius of the smaller ions and r large is the radius of the larger ion. And typically, since the cations are smaller than the anions, we can rewrite it as that gamma to be equal to r plus by r minus, that is the radius of the cation divided by the radius of the anion over there. So, that is what is called as radius ratio. Now, how do we calculate radius ratio for different kind of structures? Let us take up one example over here. Now, the minimum radius ratio for a given coordination number is calculated by considering the geometrical packing together of spheres of different sizes. What it means is the following, that is, if I want to work out that we have got a given kind of packing, that is, there is a cation and there are number of anions surrounding that. If I want to have a given coordination number, then for that particular coordination number, that is, say the coordination number happens to be 3 or 4 or 6, that is, I have got one cation and there are 3, 4 or 6 anion as the neighbors over there. So, we will try to see what are geometrical arrangements possible for them, and then try to see that what should be the radius ratio, that is the ratio of the cation to anion sizes, so that such a structure becomes stable. We will take a very simple example here, and the requirement here is that when we talk about such a geometrical arrangement, there are two things which have to be met here. Firstly, the ions of opposite charge should be in contact, that is, so this is my cation here, so this is anion. So, this cation is having 3 anion neighbors over there. And second important thing is that the ions of like charges should not touch, that means anion should not touch each other for the structure to be stable there. So, that is what we expect it to be. Okay. Now, let me take up one simple example here, that is for we are trying to calculate the reduced ratio for coordination number 3. So, what do we do is we take a small cation here, a small cation is right here, which is surrounded by 3 anions as neighbors over there. And what we have done is we just mentioned that the anions should not touch, but we have taken a structure here wherein we have purposely put the 3 anions in such a fashion they are touching each other, because we want to find out the limiting value there. Because typically the structure adopted by such a system will be the one which I showed you earlier, but in order to work out theoretically what is the limiting value of such a number or the radius ratio, we take them to be in close touching each other over there. Okay, let us understand this here, this geometrical arrangement here. We find that in this arrangement this A B is equal to B C is equal to C or C A, because they basically are the internuclear distances between the anions here. This is between anion A and B and C and C and A and so on and so forth. So, they all are equal and they happen to be 2 r minus. R minus is the radius of the anion there. And if you look at the BE is nothing but the radius of this anion over there, that is r minus there. That is one bit. Second thing what we see from here is BD. BD is this distance from the center of this anion to the center of the cation right here. So, this will be equal to r minus plus r plus, that means this will be equal to the sum of the ionic radii of this anion and the cation there. And further this angle ABC since it is an equilateral triangle, this angle will be 60 degrees, and this angle BDE here, this one here will be of 30 degrees there. And with this kind of an arrangement of anions around the cation, we find that from simple trigonometry we can see that the cos of this angle there, that is angle BDE, that is 30 degree, will be equal to BE by BD. By rearranging this, we find out that BD to be equal to BE by cos theta, that is cos 30 degrees. We just make substitutions over there and simplify. We find that r plus by r minus comes out to be 0.155. That is the limiting value. That means, if the radius ratio, that is r plus to r minus, becomes anything less than this, then these 3 ions cannot stay together, they will merge into one another. That means, they will repel each other and the coordination number will actually come down to 2 rather than 3. So, that is a limiting value for a radius ratio for a coordination number of 3. So, that is 0.155 is the limiting value for coordination number 3. Okay. Now, let us go further and see that if we do a similar exercise for different coordination numbers, we find that we come across the following data over there, which is available in all books. What we can see from here is that what are the structures adopted by different limiting radius ratios. If the radius ratio happens to be less than 0.155, the coordination number will be 2, the shape will be linear. And if it is anywhere from 0.155 to 0.225, the coordination number will be 3 and we will have a planar triangular shape there, what we just discussed here. And then going further, so from 0.225 to 414, we can have tetrahedral or square planar and so on and so forth. So, we find that theoretically we can work out what are the range of radius ratios, and for given radius ratio what will be the coordination number and what will be the kind of shape adopted by the ions around a given cation there. Okay. So, that is what is predicted by the radius ratio rules over there. Okay. Now, let us try to analyze this for the typical structures we discussed earlier. Look at this. Say we talked about 3 structures there: cesium chloride, sodium chloride and zinc sulphide, that is a Woodside structure there. If we look at that, that is the data what we had here, the cation, anion and all. We find that r plus to r minus for cesium chloride happens to be 0.9226. For sodium chloride it is 0.5359 and for zinc sulphide it is 4021, and there is a coordination number and so on and so forth. So, that is a thing what we have seen earlier, and we find that this is in accordance with what we just calculated here, what I showed in the previous table about the radius ratio limiting values there, or the ranges of the radius ratios there. Okay. Now, what you find is that as we move from cesium chloride to sodium chloride to zinc sulphide, we find that the coordination number changes from 8 to 6 to 4. Why so? Why so? Because if we try to compare the thing here, we find that the anion is roughly of the same size. 181, 181, 184, roughly comparable to each other, whereas the cation is becoming smaller and smaller. Since the cation is becoming smaller and smaller, so we have got a larger cation, we can have number of anions around that. There can be as much, say cesium is much larger, we can have 8 chloride ions around that. But when this ion becomes smaller, we come down from cesium to sodium, the ions become smaller, then the number of anions which can surround that becomes less. So, the coordination number comes down from 8 to 6, and going further, when the cation becomes still smaller, we cannot have more anions around that. So, the coordination number becomes 4 there. That is, the size of cation decreases, whereas that of the anion remains roughly constant. So, that is the reason for these 3 characteristic structures, that is, when we move from cesium chloride to sodium chloride to zinc sulphide, we find that the coordination number changes from 8 to 6 to 4. Now, that is what we just mentioned here, that is, when the cation and anions are similar in size, a large coordination number is possible, that is favorable. That is what is typically true of cesium chloride structure, that is when the 2 ions are of comparable size. But when the relative size of cation becomes smaller, it is no longer possible to maintain the cation anion contacts and also keep the anions from touching each other, because that is how things gets limited over there, and the coordination number drops from 8 to 6, and in such a case we find that the sodium chloride structure is favored as against the cesium chloride structure there. And if we go further, when the further decrease in size of cation is there, we find that the coordination number decreases further from 6 to 4, and the zinc sulphide structure becomes favored structure there. Okay. So, with this kind of rationalization, let us try to see that how do we apply these rules, how do these rules apply to different structures what we are observing experimentally. We take typical example of alkali metal halides, that is lithium fluoride, cesium bromide, sodium fluoride, and lithium bromide, and so on and so forth. We find that the reduced ratio for this is 0.57. For 0.57, we expect it to be adopting structure of sodium chloride type, and observed also is sodium chloride. Cesium bromide, we expect it to be of cesium chloride, observed the same way. For sodium fluoride, we expect, since the radius ratio is very large, 0.77, we expect it to adopt a cesium chloride structure, but what is observed is it adopts a structure of sodium chloride type. Similarly, for lithium bromide also, the radius ratio is very small, we expect it to be of zinc sulphide type, what we experimentally observed is sodium chloride there. So, we find that these rules are fine, but they have got limited applicability. And in addition to that, there is one more drawback with this rules is that they predict only one structure, which ignores phase changes, because what happens is in certain ionic solids we find that ionic solid can adopt different phases there. We will not get into details of that, but that is again a fact which is not considered by the radius ratio rules over there. Now, in addition to these, let us take one more example here, that is mercury sulphide having a radius ratio of about 0.68, it is expected to have sodium chloride structure, but it crystallizes in zinc sulphide structure. This again is a exception to the radius ratio rules over there. And the reasons for all these deviations from the radius ratio rules are that basically when we talk about radius ratio rules, we have taken ions to be hard spheres, and we ignore that the ions can get polarized there, because essentially say an ion, there is a nucleus there and there is a large electron cloud there, and if you have got a positive charge cation here, this cation can polarize this anion, and there can be certain element of covalency in that, because we do not have 100% ionic compounds. There will be some element of covalency which is not considered by when we talk about the this radius ratio rules. So, that is one reason why do we have deviations from the prediction from the these radius ratio rules there. Essentially, they are assuming pure ionic structures and ignoring covalency. So, that is one drawback or the limitation of our radius ratio rules there. Okay. Let us sum up what we have done today. What we have done today is we briefly started by reviewing the contents of the previous sessions, and then thereafter we revisited the basic aspects of crystalline solids, because we wanted to talk about the structure of ionic solids. For that to be understood, we briefly kind of recalled what we learnt about the crystalline solids in our understanding of solid state there. Having done that, we came down to outlining the salient features of structure of ionic solids there, that is what are the significant aspects of these structures there. Having done that, we came down to the specific structures adopted by the ionic solids of AX type, wherein we talked about 3 structures primarily, that is cesium chloride, sodium chloride and zinc sulfide, that is Woodside structure there. Thereafter, we brought in the concept of radius ratio and explained radius ratio rules. That means, we try to work out the limiting radius ratio for different kind of ionic structures, and then we saw that how do we correlate the radius ratio with the ionic structures there. And thereafter, we discussed its application and found that it was applicable to a good extent, but there were a lot of limitations there. And with this, we basically conclude our discussion on the structure of ionic solids. In the next session, we will go further and try to see that what are the imperfections in ionic solids there, because typically what we have in mind is that all crystalline solids are perfect, but we find that there are number of defects in such solids there. We will take up this aspect of ionic solids in the next session there. Thank you.